Good afternoon, everyone. Thank you for the introduction. It's a pleasure to be here. This work was done mainly by Eyal Ronen with some help with David Wong and Robert Gilham and non-interference of the rest. Unfortunately, Eyal couldn't make it to the conference, nothing to do with the US administration. So I drew the short straw, and I will present the talk today. Doesn't work. Beautiful. How do we move to the next one? Thank you. So we are going to talk about RSA key exchange in TLS. And I'll repeat some of the concepts later, but basically in TLS, RSA uses what's called PKCS #1 version 1.5 padding scheme. And it was once the most popular TLS key exchange option, but it has fallen out of favor because first, there were several attacks against RSA key exchange, and it has no forward secrecy. But it is still being used. So about 6% of the connections were using RSA key exchange in 2018. And because 6% of the connection used it, the servers continue to support it. There are better alternatives, but not everyone uses those. So what have we done? We investigated 9 different implementations to see if we can attack the implementation using cache attacks, if they have cache vulnerabilities that allow us to create what's called a padding oracle. We found out that out of these 9, 7 were vulnerable, 2 were not. Vulnerabilities are in all phases of the RSA, of the padding scheme handling, and this is not good, particularly because most of these implementations try to protect against this specific attack. So they try to protect against Bleichenbacher attacks, and most of them failed. So we broke 6% of the connections on the internet. Does that really matter? And the answer is that yes, it does matter. We also show a downgrade attack. So we take a connection that was not supposed to run RSA key exchange, and we downgrade it to use RSA key exchange. And every server that supports this and runs TLS, a vulnerable implementation, is vulnerable to the attack. For that, we created a new parallelization technique that allows us to run RSA padding oracle attacks in parallel, and that's the main thing I will talk about today. We do assume that we have the ability to do a cache attack on multiple TLS servers, which is realistic under certain scenarios, but frankly not many. And we use BIS to boost success probability, but this is something I will not talk. It's standard technique in man-in-the-middle attacks. So, a bit of a background on the RSA should be known. RSA, we choose a private key, select 2 prime numbers, multiply them to get a public modulus. We have a public exponent E, which is usually fixed. We have a private exponent D. We do the encryption by taking a message, raising it to the power of E modulo n. Now, this is nice math. That's what we see in first year course on computer science. Can we really use it? And the answer is no, we have some issues. And the issues are, one of them, as an example, if we have E as 3, which was once a popular choice, and message M 1000, we raise M to the power of E. This is still less than 2 to the less than the size of N. We can easily do logarithms on reals, so we can find M. So we need to use larger messages. Also, if we have a very simple set of messages that we send, if we use this approach, we get the same message encrypted the same way every time. So we are vulnerable to dictionary attacks. It's easier to detect repetitions, and we want to make sure that our M is at least partly random. And that's what PKCS #1 version 1.5 padding scheme tries to do. It basically pads the plain text and encrypt it after padding. So the padding increases the size to the RSA key length, and it adds randomization. The example used in TLS 1.2, we have a preamble that is always 2 bytes, that value 0002. Then we have a set of random numbers, random bytes that are non-zero, minimum number of 8 bytes. Then we have 1 byte that is 0, which signals the end of the padding. And then whatever is left is the original message, which in TLS 1.2 will always be 48 bytes. Now, padding oracle attacks, I'll not go into the details. It's too much maths for a talk like that. The idea is that we have an oracle, which is some sort of a mythical creature that gives us answers to questions that we cannot answer ourselves. And in this case, we give the oracle a ciphertext, and what the oracle tells us is whether the plain text that matches this ciphertext is at the format, the correct format for our padding scheme. So we'll have multiple oracles, and in the paper we investigate multiple oracles to the level of how much they match to the scheme. We can match on the first byte, we can match to see that we have at least 8 random bytes, all sort of tests that we can do. And the idea with the attack, now that we have this oracle, we start sending it a ciphertext that we generate and check the answers and try to guess the message from these answers. So we're not breaking the key, we're just breaking decrypting the message. And the typical attack has 2 steps. The first, we find a blinding factor. So if we multiply M by S modulo N, we get to a small interval. And the second step, what we do is we iteratively reduce this range. So with each query, our range gets smaller and smaller. And after roughly 2048 queries, we'll get a range of size 1, and that will give us the message. Or it will give the message multiplied by a number, and we just need to multiply by the inverse of that number, and we find the number. So this is how it works. The maths is a bit more complex, but we will ignore it for now. So now, what we want to do with that? We want cookies. Why do we want cookies? Because if we get the cookie that of a session cookie for the user, for the connection to the bank, we can use that to masquerade the user. And these cookies are sent at the beginning of every TLS connection. So we have a simple attack against that. We listen to the network. So we have our attacker listening to the network. They get the TLS handshake first message. They use Bleichenbacher to decrypt the pre-master secret, which is used to encrypt the whole exchange. And then use it to decrypt the first message, and we got a cookie. And that's beautiful. And as I said, it allows us, let's see it graphically because it looks nice, and thanks to Eyal. So we have our bank, we have our user. Cookie Monster listens to the communication, runs the Bleichenbacher attack. It's 2,000 messages there, and we need to have, of course, our cat listening to the cache to get the oracle, and we got the cookie. Now, we got only 6% of the connections this way. So now we want to get more of those. So we use downgrade attack, and the idea is very simple. We have our cookie monster. Instead of passing the messages, it changes the messages. It tells the server, our client only support RSA key exchange. Please use RSA key exchange, and the server will comply with it, and we'll get everything working. So as long as the server supports RSA, it works. We can do the downgrade for a TLS 1.3. It's not our ID, but it can be done. We require active main in the middle, but it's a plausible attack model. So do we have the cookie? And the answer is unfortunately not. The reason that we don't have the cookie is that our browsers wait for 30 seconds for connection creation. And if the connection doesn't happen in 30 seconds, they'll drop it. At least most browsers do it. In these 30 seconds, we need to have 2048 sequential queries. Unfortunately, we have time for about 600 if we are lucky. So we need to do something better. So what's something better is to do parallel downgrade attack. We assume that we have multiple servers, and some companies will reuse their certificates on all the servers because they want to have the same, they want to be able to shift communication between those. So we have that working, and we now attack all of them. So the idea is we want to parallelize this across all these servers. And we treat each server as an oracle, and we know that we can do parallelization. So do we have the cookie? And the answer is, again, unfortunately, no, because we need 2048 sequential queries. Each query depends on the results, on the earlier result. We can't just divide this to 20 servers and get them in 200 queries each. And again, we have time for 600. So now what we want to do is a parallel padding oracle attack, and the idea is that the idea is based on if we start this padding oracle attack, and we start bounding the interval, we get at some stage to a small interval. It is not large enough to break, small enough to break it to brute forcing, but it's smaller than the full area. And we run it in parallel, multiple attacks. What we'll have is multiple different intervals. And the beautiful with the mathematics there is that this fits well within the Boneven-Kattesan hidden number problem. So what we have is basically is an instance of the hidden number problem. We take this hidden number problem, we create the instance of hidden number problem, convert it to a lattice problem, standard technique, and solve, and we get the results. So again, we have our cookie monster listening to the connection between the server and the client. It breaks this connection. Instead of returning the response to the client, it runs multiple queries on multiple servers. At the end, puts everything into a lattice, and we have a cookie. So we have new techniques for doing microarchitectural padding oracle attacks. I haven't talked about the cache attacks themselves. So if you're interested, look at the paper. We have a new parallelization technique that downgrades the connection to RSA and manages to do it within the time. And we disclosed it to everyone. Everyone patches their code with some level of success. Everyone created a CVE, so it looks like a fuzzing paper now. And the other issue that remains is that everyone tried to solve these cache attacks or protect against cache attacks, create constant time code for RSA padding schemes. Most of them did not get it. The rest you can find in the paper, and I will be happy to take questions.
I just wanted to get you to say a couple of words about the active man-in-the-middle attack. Does it have a particular signature that could be looked for to see if somebody's trying to employ that?
The active man-in-the-middle attack? Well, for the active man-in-the-middle attack, what you'll get a client that wants only to communicate over RSA key exchange, which is not standard or not supported by many. The problem with that is that if people were willing to not accept these connections, then we wouldn't have had this problem in the first place. The other thing is that again, for the client, we rely on the beast attack, so we still have some site trying to run this connection at the client. You'll get many of those failing connection at the servers, so there are some indications if anyone wants to look for those.
I'll ask a question. Can you say a little bit about where you see the co-location on the server side as being the sort of plausible scenario?
Well, this is a difficult problem to solve. We've seen many papers, even recently, showing that co-location is possible. I can't say what the likelihood is to get 5 or 6 co-locations concurrently. So yes, it's difficult. It's not an easy attack. I assume that most servers will have problems that are more pressing and more important to solve before we try these, they address these.
Hi, briefly you said that there was a way you could do this in TLS 1.3. As far as I understood, in TLS 1.3, the set of supported encryption schemes are signed by both sides. So I was wondering, wouldn't that stop the downgrade attack?
In both cases, it's assigned by both sides. And TLS 1.3 doesn't support RSA key exchange. So now that's why we need the YAL here. As I don't remember if what we did was downgrade to 1.2, or we used the same certificate for that we break with RSA1 with TLS 1.2 under the assumption that they use the same certificate for RSA signing.
Thanks.
All right, let's thank you, Wolfgang.